Welcome to my YouTube channel. Dhanesh here. So in this video, I am going to discuss about Perceptron. See, Perceptron means we can call it as an artificial neuron. Perceptron, it's also known as an artificial neuron. It is so it's artificial neuron. Perceptron means so we have biological neuron, and this is perceptron means it's an artificial neuron. A perceptron is a neural network unit or an artificial neuron that does certain computation to detect feature in the input data. That's what a perceptron do. A perceptron is a neural network unit or an artificial neuron that does certain computation to detect feature in the input data. And the perceptron was introduced by Frank Rosenblatt in 1957. It is introduced by Frank Rosenblatt. I don't know the pronunciation is correct or not. See, Frank Rosenblatt is the scientist who introduced perceptron in 1957. See here, if you want to see how it is, before how a perceptron works, so before that I can show you the this is the simplest architecture of a artificial neural network. See, it consists of the input layer, the hidden layer, and the output layer. Input layer takes the input. Inside the hidden layers you will get the computations or calculations will happen, and the output layer will give you the output. The circles represents the node. In this architecture I have shown, the circles represents the node. So this you will understand, it's easy. All these circles we call it as the node. The the black arrows, it is the weight of the network. These things you may be familiar. So this is the the simplest architecture of a neural network. So here the circles represents the node and the black arrows represents the weight. Now I want you to tell you, see how single perceptron looks like. I can tell it as like you have like this. You can represent, for example, you have the bias. So this we will take it as the value of the bias, always take it as 1, and the weight of the bias we will take it as b. Then another input, you have x1, here you have x2, you have x3. These are all the inputs coming, and the weight of these inputs we can take it as this is we are b, or we can take it as w0, or this w1, this one w2, this one w3. These are all the weights of the network, weight of this inputs. Now it will be summed and you will get the weighted sum. This we can take it as sigma. Then you have the activation function here. This is the activation function. You can use sigmoid, ReLU, or a hyperbolic tan. So here you will get the output. This is the thing exactly happening inside a perceptron or artificial neuron. So here this is the weighted sum. This is the activation function. This is what happens in, and this here you will get the output. This is what exactly happening in a perceptron. See, in a perceptron, only two things happening. First thing, it is the weighted sum, the sum of the weights weighted into the input, weighted sum. The second one is squashing the weighted sum with an activation function. These are all the two processes happening inside a perceptron. Once again I will repeat it, so just you can hear it. See the two steps happening inside a first perceptron or artificial neural network. See the figure I have shown you. That's the way you will represent a perceptron or artificial neuron. So the first thing, there are two steps happening inside a perceptron. The first one is that it will calculate the weighted sum coming to a particular node, coming from a particular node. Second point, it will squash the weighted sum with the activation function. So what is activation function? Activation function represents the state of a node. See, activation function determines whether a particular node should be activated or not. There are different types of activation functions: hyperbolic tan, sigmoid activation function, ReLU. All these are all different types of activation functions: ReLU, sigmoid, tanh. These are all different types of activation functions. Activation functions introduces non-linearity in the neural network. That means if I am using sigmoid, which is the common activation function we use, its value changes from 0 to 1. Sigmoid function. For hyperbolic tan, it is -1 to 1. So any value between 0 to 1 can be there in the sigmoid function. From -1 to 1 can be there in the hyperbolic tan. So like that, this introduces non-linearity in the neural network. So the sigmoid functions introduces non-linearity in a neural network, and it determines whether a particular node should be activated or not. So that's what the activation function do. In a perceptron, there are two things happening as I discussed. First one is it calculate the weighted sum. Second, then squash it with the activation function. Squash the weighted sum with the activation function. So these are all the two things it's happening inside perceptron. See, if you compare your perceptron with your biological neuron, in your brain there are trillions of neurons are there in your brain. If you compare the biological neuron, see this is I can take it as the biological neuron and our perceptron. If you are comparing these things, you will get like this. See, in your biological neuron, see how a biological neuron looks like. It is somewhat, I will first draw the figure for this. This is what a biological neuron looks like. See, this is the you have this this is the shape, I believe, and you have the axon. See, this is the shape of a biological neuron. This we call it as the axon. This is the nucleus, and these things you call it as the input, and this is the output. These two is the output. See, the input we call it as the dendrites. This we call it as the dendrites. This is the way the biological neuron input, it is taking through the dendrites, output is through this, axons, the end portion of the axon. This is known as the nucleus. In the same way, if you compare it with a perceptron, your biological neuron and perceptron. This is biological neuron. Here I am taking perceptron. Then the comparison will be, you have the cell nucleus in biological neuron. We call it as soma. The cell nucleus, we call it as the soma. The corresponding thing in the perceptron is the node. I told you, the circles represents the node. You have here the dendrites. Here you have the input for that. Here, and one more point I need to tell you, two biological neurons are connected together by synapse. The connection, we call it as the synapse. For this, we have the weight, that black arrows, it represents the weight. And you have the output, we call it as the axon. And here you have the output for this. This is the comparison between biological neuron and a perceptron. Now, what will happen? What exactly is happening inside an artificial neural network? See, I told you, for example, I am giving you a simple, neural network. Then inside the perceptron, what's happening? The neural network, as I told you, it looks like this. See, I am drawing it. It should be, you have the inputs. It's like you can take it as you have inputs like x1, x2, x3, and the bias we take it as 1 usually, and the weight of the bias you can take it as b. So here it is w1 is the weight of this. This is w2. This is the weight, it is w3. This we take it as b. This is the weight of the bias. And it is coming to our, the weighted sum. Here all the weighted sum will be calculated. That is I am taking it as sigma. After that, we will squash it with a activation function. I am taking it as sigmoid is the activation function. Then we will get the output y. So this is this is a perceptron. This is exactly what's happening inside a perceptron. Then I am writing the mathematical steps for this. So what are all the mathematical steps involved in this perceptron? So first I will calculate the weighted sum. So the weighted sum, see, here also, if you in the figure, whatever I have drawn, the x1, x2, x1, x2, x3 represents the input layer, the activation function, and the weighted sum, those calculations, it's happening in the hidden layer. So this is the architecture. The squashing of the input and the weighted sum, the calculations, it's happening in the hidden layer, and the output we will get through the output layer. So that's what the different layers. So the mathematics behind this, you can write it as, say, z should be the weighted sum. I am taking it as z should be, it is w1 x1 plus w2 x2 plus w3 x3 plus b into 1. This is the weighted sum. Now I am calculating the output. For that I need to, the output y should be the sigmoid function of a sigmoid function. I can write it as sigmoid of this weighted sum z. Usually we will denote it as sigma of z. See, the sigmoid function sigma, this is the formula for this, 1 by 1 plus e raised to minus x. Then instead of x, what you will get when you apply the sigmoid function, what you are going to get here is, so your output will be is equal to 1 by 1 plus e raised to minus az. This is the output. So this is what happening inside a perceptron. There are two processes. One is calculating the weighted sum, then squash it by using the activation function. Activation function introduces non-linearity inside a neural network. It decides whether a particular node should be activated or not. The same thing happening inside your biological neurons as well. See, based on a particular situation, which neuron should be activated, all these things, it's all programmed, from your childhood. What are all the inputs? It's happened, it's taken inside your brain, inside your neurons. Based on that, you respond to those particular situations. The same thing. So we have the, based on the activation functions, it's our perceptron will respond. See, one more thing I will share in this video. Most of the neural networks, some back propagation algorithm, all these aspects, when you decide, you will calculate the derivative of the sigmoid function. So that you need to apply the quotient rule. If you want, I can tell you the derivative of the sigmoid function. You can apply the quotient rule, and at that time, if you calculate the derivative, you will get like this. I will give you that formula for that. It is, if sigma is the activation function, if you calculate the derivative with respect to x, sigma is 1 by 1 plus e raised to minus x, then the derivative, this formula you will use in the back propagation algorithm in neural networks. So I have those algorithms in my playlist, a separate playlist for detailed study for the back propagation algorithm is there in the playlist. You can see that there, when you calculate the derivative, you will get sigma into 1 minus sigma. This formula, we are using it in the back propagation algorithm. And this perceptron are the two types. There is single layer perceptron and multi-layer perceptrons. That's another thing you want to understand here. One is the single layer perceptron. Second one is the multi-layer perceptron. Single layer perceptron means there is only one layer in the hidden layer. Only one hidden layer. Here you will be having multiple hidden layers. See, I have shown you in this architecture you have two hidden layers, so that means it's a multi-layer perceptron. So here you have if you have only one layer in the hidden layer, then you have only one hidden layer, it's a single layer perceptron. So perceptron means artificial neuron. And the main thing you need to understand is that architecture of the perceptron. I have drawn the diagrams for that. And what's happening, what is the mathematical process happening, it's inside a perceptron is you are calculating the weighted sum and squashing it using an activation function. So that's all about perceptron. Thanks for watching.